I haven't.
No, that's Uli's.
That's Uli's. Okay.
The slides for the portable fourth assembler talk are not ready. That's why I'm presenting a different talk.
Well, he's swapping talks. I think that we can follow it.
Region-based memory allocation. So the problem is memory management. In particular, how do we reclaim no longer needed memory? And there are several answers to that. The classic fourth answer is, of course, we don't need that kind of complexity, but actually I find I need it. So of course, the good old fourth way of using a lot, and we can reclaim space only in last in, first out manner, which is, isn't always satisfactory. Then the standard, the 494 standard, gave us allocated free, and we basically this means that we have to free, or we can free memory after the last reference is consumed. And the problem is that this is quite error prone. You can have banking references. Basically, if you free too early and there's still a reference around, and then later the reference is accessed, this is an error. It can get really bad if, for example, we had another allocation afterwards, and that allocation got the same memory, and then we store there, and basically some completely unrelated piece of data gets corrupted by the store. So we don't want that. And of course, we can also error in the other direction and forget to free, and then we get a memory leak. And there are really perverse things like Netscape basically leaked lots of memory, and there are now tools that tell you, yeah, you're leaking this and that memory at the end. So what did the smart people who programmed Netscape do, or Mozilla nowadays? They actually made a linked list of all the allocations they have, and just before they finish the program, they de-allocate everything. So what's happening is all that leaked memory gets paged out onto disk, and if it then basically finished the process, everything would be okay. But instead, it goes through the linked list and frees everything, and this pages in all this memory, and which takes several minutes before the program actually terminates. One of the perverse things about using tools, you gain them. Anyway, so what can we do with allocate free? There are, to make it less error prone, there are various disciplines of programming with allocate and free to make it work better. And I have not found anyone that I found satisfactory, but some of them may actually even cost performance. For example, one way to deal with, to know about when the last reference is consumed is to actually get a better idea of, to make extra copies. So you know that this original copy now no longer has a reference, and the other copy has a reference, but this is managed in a separate way. But of course, doing the allocation for this extra copy and copying the stuff over costs performance, and which is not, so basically one of the arguments for doing explicit freeing is that it's supposedly costs less performance than some more automatic ways of reclaiming memory. but if you count in the workarounds you do, it may actually not be the case. And even without all these workarounds, there are a number of allocate-free packages that are pretty slow at what they do, and there used to be C programs that spend, I don't know, 30–40% of the time in allocated free. Well, of course, in C it's malloc and free, but it's the same thing. In the meantime, the allocators have improved, so now it's not so slow. So, another common answer is to use garbage collection, which is very convenient and very nice, but the question is whether it fits in Forth, because it's the implementation particularly, so it's very simple to use, but the implementation is complex, and especially we have a number of requirements that we want to have and need to have in Forth, and that are not really, don't go well with garbage collection. Real-time requirements are a particular problem because there are, well, relatively simple implementations of garbage collection stop the world. Then you get a pause of whatever time, number of milliseconds or more, and then it continues, and you don't want that in a real-time system. Garbage collection doesn't combine well with multi-cores, because when you stop the world for all the cores, it's not so great either. You first have to find safe places in all the threads and all the cores, and many garbage collection systems assume that they have perfect type information. They know exactly what is an address and what isn't an address. And in Forth we don't have that information. And there are solutions for each of these problems, but I don't think there is a solution for every one of them. Not sure. But in any case, if there is, it's going to be extremely complex. I have written a Forth garbage collection library, and this has been available since 1999. And it basically solves this one. It doesn't deal with multiple threads and multiple cores. It doesn't deal with real-time requirements. And it has been used a little bit, but not much. So this brings us, oh yeah, there's another one, reference counting. So that's another automatic reclamation technique, which is not quite as nice as garbage collection. It doesn't deal nicely with cyclic data structures. So if you have the cyclic graph somewhere, it won't become reference counted. You have to do something on every time you duplicate an address, or when you delete an address, you have to update the reference counter. That's slow. You need to do a special version of cube and drop and store and other things that can cause additional or copies of addresses, or delete copies of addresses. So I think this is not a solution for Forth. At least not the general one. So there's an idea that has been around in more general computing for a long time, which is region-based memory allocation. It works like this. We can create a new region, and then we allocate a number of things inside this region, and we can have several regions at once. We can allocate some things to one region and some things to another region. So that's why we pass a region ID to this region alloc. And eventually, when we are done with all the data in a region, we do a free region, and all the stuff that's in that region is freed at once. So we don't need to keep track of individual data in that region. It is freed all at once. This would be a minimal interface for regions. I'm going to talk about a different interface later, but let's first see what we can do with regions. So the idea is that we use one region for every bunch of things that die at the same time. For example, if we implement a compiler, we could have a region for the stuff that lives while we process a basic block, and another region for the stuff that lives while we process a definition, and so on. And so when we're done with the basic block, we free the block region and create another one. When we are finished with the definition, we free the definition region, and so on. In a web service, we could have a region for the HTTP request. When we have finished working on the HTTP request, we free all the memory at once and are ready for the next HTTP request. Another way of looking at the usage is that the programmer we can give the programmer control over whether he wants to use fewer regions, which is more convenient. So basically, the programmer just has, maybe in the extreme case, just one region, and he allocates into it until he's done with everything, and then he frees everything at once. But in that case, he might get lots of stale data that's still bad wood that still consumes memory but isn't actually no longer relevant. And when he finds that this is too much memory consumption, he can introduce more regions and to get finer grained control and have less bad wood. So yeah, that's what's here. So we start out with few regions and add more if necessary. So yeah, regions sound good. Why haven't we seen it in Forth yet? And I've thought about regions several times, and every time, basically, if we look again at this interface, I thought about this kind of interface, and every time, after a while of thinking about it, I thought, well, the problem is that we get lots of stack juggling because we have to pass this region ID around. And that's basically what turned me off regions every time. And this time around, I thought, well, let's do some, maybe I should talk about the implementation first. But anyway, I thought about a different interface, and we'll get to the new interface in the next slide. In the meantime, here's another good reason why regions are a good idea. Here we see how an implementation might look. For each region, we allocate a block of memory. So here we have our example with the compiler, where we have a region for blocks, a region for definitions. And so we allocate a block of memory for this first region, a block of memory for the second region. And within a region, we just, if we need 50 bytes here, we just give it out. And basically right afterwards, we can have the next block, so we don't have any overhead within these blocks. Once we run out of space within such a block, we allocate another big block, and then allocate from there, and we have another pointer back to the first block, and our region implementation now points to the newest block, and we can continue allocating, and if we run out of space here, we can get another block, and so on. And when we are done, we basically follow all these pointers and free all these blocks. So when we free the region. So if you ask for memory and there's not enough space in the region, it will start a new region. So you'll always get contiguous memory. If there's for a given region there's not enough space. So if we, for example, here we had the example, basically we needed this much space, and there was not enough there, so we asked for a new block. Does this answer your question? Yeah. I mean, there are other ways of dealing with things. For example, you could actually try to make use of that additional space in some way, which the question is, does it really pay off or not? And I think people have thought about implementing. You have to nevertheless decide what's the biggest contiguous memory you might want, because that your region size has to be big enough to. Well, my block size, you mean? Well, actually, if no, it doesn't, because when you ask for a very big memory, it'll make a new region. If it asks me for a big memory, I could just get a big enough block for it.
You could also say that if you ask for more than 16 pages or so, you use a different allocation mechanism, gives that a new block.
I mean, this is just one, and one implementation of the region idea is glibc's obstacks, and it describes pretty much this kind of thing. And it says when there's such a big allocation request, it just allocates a big enough block. And I think that the block size they use, the default block size is 4 kilobytes. So now on to the improved interface. The heart of the improved interface is also at the heart of this piece of these lines. So it's the with region word, and I pass a region ID to with region and an execution token, and the execution token actually doesn't, so I can pass in additional stuff here and get out additional stuff there, but in itself it doesn't consume anything. And the region is an implicit parameter within this xt. And when I do an allocate, while executing, while in this region, it will actually allocate from this region ID. And when I do a free, it will ignore it. So the idea is I tag on to allocate and free, because then somebody can write, or we can use a library function that's written for using allocate and free, and actually still use it with region-based allocation and make it more convenient. So, the other words, basically new region, free region, we have seen that earlier. There's also a do region, which is basically a wrapper for new region and free region. What it does is it takes an execution token and creates a new region and performs the execution token. It creates a new region, pushes that region on the stack, and performs the execution token. And when do region is left, it frees the region, the free region. And why do we need do region at all? The point is we are guaranteed to free the region even if there's some exception. why don't we do do-region and with-region in the same wrapper? The reason is that if we want to deal with several regions, we want to have with-region as a more we probably want to have more with-regions than do-regions, and want to have it at a different level. An example of all of this is here. We have, that's what we have here is a quotation. So who knows what a quotation is? Oops.
Maybe the lower connector.
This lower one?
Yes.
Yeah, you know.
Perfect.
So, nobody knows what a quotation is. Okay, a quotation is a column definition that's basically written in lines, and an unnamed column definition that's written in lines. So from here to here we have a column definition, and we get the execution token of the column definition out of this quotation and pass it to do-region. Who has understood that?
Just one question with the quotation. Is it going to be sitting only in temporary memory? Can it be only used once, or how often can you use a quotation?
Well, actually, the quotation itself is just a piece of code, so that's stored as code somewhere, and you can use it as often as you want. So you can dupe the XT and store it somewhere and use it as often as you want.
Yeah, but could also, for example, have a region-based quotation memory and just drop all the quotations I don't need anymore?
Not clear what you mean here.
Like lambda expressions in other languages.
Actually, the thing, what the quotation doesn't do, what the lambda does, is lambda builds a closure which contains some additional data, and we don't contain any data, so we only contain code. So basically that code is stored somewhere statically, and you don't need to allocate any memory for it. Anyway, back to this. So basically what you could do is you could say colon no name and the same basically write the named colon definition and then write here tick and the name of the colon definition and pass it to do-region, but writing it inline is a little bit more elegant. And here inside we have we tick word using allocate, which is a word that uses allocate. I'm not specifying anymore. And basically that word produces some data, probably on the stack. We pass the execution token of that word to with-region. So the allocate in this word, or the allocates in this word are actually using the region that we pass here to this with-region for allocation. When we are done with that, we pass the result of this word to use result. And now that we no longer need the result and the memory that that result occupies, we can actually free all this stuff. So we get to the end of this here and do-region freeze the memory. So this would be one use of the new interface, and particularly you don't see it here. I'm preparing another talk about strings that's more clearly visible. Basically, you don't have to pass the region explicitly to allocate. That's the the main benefit of this new interface. So, yeah, conclusion is that region-based allocation is more convenient than free. It is compatible with multi-cores in real time, which is really hard with garbage collection. And the question is, why have regions not taken over the world? I think that for fourth, there are two things. Of course, many fourthers say we don't need this kind of shit. It's just too complex. We are doing fine with a lot. We don't need any allocate. We certainly don't need regions. For others like me, it has been always the interface has never been attractive because I need to pass the region explicitly. Now, I think it may be a good. So with the new interface, I passed the region implicitly. I think we have I've solved this issue. Regions haven't taken over other languages because essentially garbage collection won. So anybody who wanted something more or better than allocate free usually went to garbage collection, and so regions basically were squeezed out. For some reason, regions haven't taken over C, but maybe this is also they have malloc in the standard and regions not in the standard, and maybe that's the reason. But that's
well, there is Objective-C. They use
regions. Okay, Objective-C uses region. So it has at least taken over Apple.
Question from someone who's naive and not that advanced with fourth. When you had the use region, it was combined with the execution token of a word, so that it would use the region for executing that word. Naively, you might think, well, why not just have a word where we just say use region, and from now on, we'll use that region until you say use another region or free that region. Why do you combine it with an execution token?
Actually, yeah, the thing for these kind of interfaces is so like you do it with base. In base, you set the base, and then you use the base until you use another base. And my experience with that is it's always problematic to actually get the thing to when you go into something, you need to save it, and later you need to restore it, and so on. These things are easier with these kinds of wrapper interfaces, in my experience. So I've in the last few years I've pretty much picked up using these kinds of wrapper interfaces. Yeah.
On the conclusions slide, you say regions are compatible with multi-cores in real time.
Yes.
Can you explain how?
Well, it's basically I can do if I do regions in one thread on one core, it doesn't really concern the other threads. Doing regions across threads is probably more interesting. I'm not sure if one would actually do that. So I guess
you're implying that it's a region per thread.
At least I would use the allocation only for one thread, yes. And
that means the region is not a mailbox.
Yes. Would be interesting to consider other options, but for the first go, I wouldn't go there.
Yeah, the general idea of multi-core fast allocation is to have one pool per thread to allocate from, and when you have regions, then you have one region per thread to allocate from. So
well, several reasons, but certainly not a region that crosses threads. And for real time, I think, well, I mean, it's, of course, the question is whether free region is actually real time compatible, but I think at least it is more, it's at least as compatible as the free of allocate free. So if allocate free is okay with real time, so is regions, I think. Yes?
Well, Objective-C allows you to nest the regions if you feel like it. So you can have one global region for some stuff which you need to store permanently or which you need for the whole application life. But if you're going in deeper and there's just some tiny thread which you're going to start only for a brief period of time, that you can just, you do not have to create an own region for it, just create an unnamed nested region, then just read right away after it. Have you considered making something like this so that like every region would have a little pointer if there's a nested region, and then you can just propagate the free, and but you can also just drain a part of the region. The idea behind this is that the overall memory consumption is not too big, that you can get down to smaller regions in the end.
Not clear how.
Okay, I'll think about a good example.
Okay.
I was thinking about something similar, and it sounds, a nice example might be when you're maybe allocating a chain of resources. I need to get a driver going, and I want some memory for that, I want to open a file, and any one of these things can fail, and I don't want to have to de-allocate each thing in reverse order depending on how far I got down the chain before I get a failure. So I just make a region, and then I go all the way down my stack, and if it doesn't happen that I manage to reach the end of my allocation of resources, I've just got one exit point. I just kill that region, and I don't need, and but then you can have a hierarchical system as you get more sophisticated code. Allocating a single resource might actually be several sub-allocation of resources. You can just go in and out, but the point is the exit point can be quite simple. It's always just kill that particular region.
Yes. Well, that's actually pretty easy.
How do regions work together with throw?
Yeah, that's the point here. So basically, when you exit, so if you use these words, when you exit when you do a throw out of this region, it will automatically make the previous region the current region, and when you exit from do region with a throw, it will automatically free the region. So whether you exit through a throw or regularly, in both cases it will this will work. That's why I like this kind of wrapper interfaces.
Okay, but don't you have to build this into the throw code then?
No, I have to build it into do region and with region.
I believe you. Second question, you didn't say anything about the memory allocation mechanism. That is underneath the region mechanism. Okay.
So I could, simple first implementation would work on top of the allocate that's in the fourth system, and I could then, if I wanted to do more, I could maybe go to the operating system with mmap or whatever.
Yeah, I was going on from that. How do you decide the region size?
Well, that's for the you mean, let's see.
Because when you do a new region, it's basically calling old allocate.
Yes.
So you're specifying a size.
Yeah, so...
And that size must be larger than the largest contiguous block you ever require.
No, it has to be... So basically, so if I have a new, so let's say I have a new region here, this is the first one, The first thing I want to allocate from that region, basically I allocate the block size, for example, for obstacks, and I guess I'm
So the region is only physically created on the first allocator.
That's at least
Right.
one option.
Yeah, okay, understood.
Pretty.
But my second remark is that
But
when you-
even if it isn't, I mean, if I have a block here that's 4K long,
yeah,
and I ask for a 20K thing, then I allocate a 20K block and
right, separately.
Yeah.
Yeah. But the other thing I would say is when you say garbage collection 1, I've just recently started fiddling around with Python, and it's awfully easy to get memory leaks in Python, which has a fully automatic garbage collector, and thus it should be impossible to have a memory leak. If you actually Google help Python memory leak, you get about 1 million extremely complicated answers, which indicates to me that I may not be the only person with this problem. So I suggest you give the paper in the next Python conference. I think you would be very successful.
Certainly there is, even if you have garbage collection, you can, if you don't, basically what garbage collection does, it looks around memory, so it starts out with a set of roots, which is basically global variables or something like that, and follows everything it can reach from there, and everything that it can reach from there is supposed to be alive. And what can happen is you allocate huge data structures and you still point to them even though they are no longer needed, and then you have memory. So if you then store null or whatever in the root, you actually
But another consequence of this continuous creation and freeing of memory blocks is that the memory becomes fragmented. And then when you look at the memory usage of the application, it tends to slowly grow over a long period of time until it gradually levels off. So the actual memory allocation over a few days is actually not easy to determine in the first few minutes of the application running.
So, yeah, any further questions?
Thank you, Anton.
Yeah, thank you.
Sort of 8 extra minutes. What? Okay.